Alrighty, how are y'all doing today?
Doing well.
Cool deal. Well, it's our review session, so go ahead and start asking questions.
I have a web work problem. Can you work it?
Absolutely. Let's see.
It's homework 23, problem 3.
Homework 23, problem 3. All right, let's see. Student progress. Flynn. 23, problem 3. All right, let me share my screen here. So I'm using Mr. Flynn's numbers and all that kind of jazz. And it tells us, so we have a circuit that looks something like this. So let me change colors there. And this is, call it VS, and VS is given as 152 angle negative 131 degrees volts. And we are asked to find the complex power absorbed by all of the elements. So what's the first thing that we need to do with this problem? Our complex power equation is this guy, right? Where we have the RMS phasor voltage times the complex conjugate of the RMS phasor current. But we were not given the RMS phasor voltage. We were just given the phasor voltage. So what's the first thing we need to do?
Find the RMS voltage
Sure.
for the voltage source.
Yeah. So that is going to be, dang it, simply Vs divided by the square root of 2. Only change we need to make. So 152 divided by root 2 is 107.48, and we'll keep that angle of negative 131 degrees volts RMS. So now we're good to go. Okay, so let's see. So I'm going to need to know this quantity, which I'll call V4, this quantity, which I'll call VL, this quantity, which I'll call V10, this quantity, which I'll call VC. Then I'll need to know this quantity, which I'll call IC, this quantity, which I'll call IL, this quantity, which I'll call I4, and this quantity, which I'll call IS. And I'm drawing IS flowing down because we're asked to find the complex power absorbed. So I need the current flowing through the positive polarity terminal. And I'm not drawing a current I10 because IC is exactly equal to I10, so that would be just, redundant. All right, so those are the several different quantities that I'm going to need to find. So does anybody have any suggestions on how I might go about finding some or all of them?
You use mesh analysis to find the currents and then use Ohm's law to find the voltages.
So we could go that route, but let's say like a problem like this could very well show up on your exam, and on your exam, you're not going to be able to use mesh analysis because your calculator can't solve a system of equations like that. So we could solve it using mesh and then using what's called Kramer's rule to solve this system of equations, but that's not nearly the easiest way to go about this. So what I would suggest is one of two routes. We can either do a source transformation, because we have a practical voltage source on the left-hand side. And if we do that, we will be able to figure out the current IL and the current IC just using current division. And then we can use Ohm's law to figure out VL, V10, VC. Then we could use KCL to figure out I4, and then Ohm's law to figure out V4. So that's one route. Another route is we could leave the circuit alone and use voltage division to find V4 and VL, and then another instance of voltage division to find V10 and VC, and then use Ohm's law to find all of our currents. A third way to do it would be to find an equivalent impedance, which would allow us to solve for I4 and V4. So if we find the equivalent impedance, we can find I4, use Ohm's law to find V4, and then from there we could do KVL to find VL. Anyway, there are lots of different ways that we can go about doing this. So which way floats you guys both the most? And again, we're trying to avoid doing mesh. But now that I think about it, we could do a one equation, one unknown nodal analysis as well. So just
Source transformation.
Yeah, 14 different ways. Source transformation. All right, let's run.
Sounds good.
Okay, so source transformation, we are going to have then my pen thing will work. There we go. Current source directed up in parallel with our 4 ohm resistor in parallel with our J5 ohm inductor in parallel with our 10 ohm resistor, which is in series with our minus J5 ohm capacitor. This current IS as an RMS phasor is simply going to be Vs divided by 4 ohms, which will be 26.87 angle negative 131 degrees amps RMS, excuse me. So while we have this, I want to draw the currents and voltages and stuff that we can find directly from this representation of the circuit. So we can definitely find out what VL is. We could find out what V10 is. And we could find out what VC is. Those are all of the voltages. We won't be able to figure out what V4 is because we've changed the position of the 4 ohm resistor. With regards to our currents, we will be able to figure out what IL is and what IC is. And once we know those pieces of information, we can actually work backwards to find out everything else that we're missing. All right, so doing current division, IL is going to be our current IS, 26.87 angle negative 131 degrees amps, times, it's going to be kind of a big thing here. So we have 3 branches that are in parallel. So we're going to have all of those branches represented in our denominator. So 1 over 4 ohms, 1 over J5 ohms, and lastly 1 over 10 minus J5 ohms, where 10 minus J5 ohms is the total series resistance of our rightmost branch. And because we're trying to find the current through the inductor, we need to have 1 over the inductor impedance here in our numerator. So this is our equation, and we'll toss this bad boy into our calculator. Okay, so let's see.
Hey, Dr. Hartman,
Yes.
is for in the brackets in the denominator, is that a 10 like multiplied by J5, or is that supposed to be a plus?
It's 10 minus J5.
Oh, minus. Okay.
Because those 2 elements are in series, so we can add their impedances together.
Oh,
So
okay.
10 ohm plus minus J5 ohms is 10 minus J5 ohms.
You're right. I forgot. I didn't see the negative on the J5.
No problem whatsoever. So this gives us 14.653 with an angle of 164.866 degrees amps RMS. So now we can find out what IC is using a very similar expression. So our denominator is going to be the exact same thing. My question to you guys is, what's supposed to go in the numerator here?
And 10 minus J5 ohms? 1 over 10 minus J5 ohms?
Exactly right. 1 over 10 minus J5 ohms. So in the numerator is always the 1 over the branch we want the current through. And the denominator is 1 over all of the branches. All right, so n minus 5i, I get 6.553 angle negative 78.568 degrees amps RMS. Okay, so my question to you guys is then, now that we know IL and IC, can we figure out what I4 is in our original circuit?
Yes, sir.
Yeah, so what would we have to do?
Add those two together to get I4.
Yeah, so applying Kirchhoff's current law at this node tells us that I4, the current going into the node, is equal to IL plus IC, which is the current exiting the node. So from this, we can say that I4 is equal to IL plus IC. And let me go ahead and just add those guys together. $13.106 angle negative 168.568 degrees amps RMS. Let me just double check that. That's X. Yep, okay. We could also then see that IS is just negative I4 which will be 13.106 angle positive 11.432 degrees amps RMS. So now that we have these four currents, we actually have all the information we need to solve the problem. We could go through and find the voltages using Ohm's law, but it's not really necessary. And so we've used some of these relationships before a couple of times, but I'll just be clear about what I'm about to do. So the complex power S is by definition the RMS phasor voltage times the complex conjugate of the RMS phasor current. And I can say that the voltage is simply the RMS phasor current times the impedance. So this is going to give me the magnitude of the phasor, RMS phasor current squared times the impedance is the complex power. I know all of my impedances and I know the current flowing through all of my impedances, so I'm good to go. Does that make sense?
Yep.
Yes.
All right, so from this, let's start with our 4 ohm resistor. So S4 is going to be the magnitude of our current I4, which is 13.106 amps RMS squared times the impedance, which is 4 ohms, is 687.069 plus J0 volt amperes, because the complex power absorbed by a resistor should be purely real. The complex power absorbed by our inductor is the current flowing through the inductor, 14.653 amps RMS squared times the impedance of our inductor, which is J5 ohms, which is 0 plus J 1073.552 volt amperes. For our 10 ohm resistor, it's going to be the current that's flowing through our 10 ohm resistor, which is IC. So we'll have 6.553 amps RMS squared times 10 ohms, which is 429.418 plus J0 volt amperes. Let's see, C, complex power absorbed by our capacitor, is going to be IC 6.553 amps RMS squared times the impedance of minus J5 ohms, which is going to give us 0 minus J 214.709 volt amperes. And lastly, the complex power absorbed by our source is going to be the voltage, the RMS voltage drop over our source, which is 107.48, angle negative 133 degrees volts RMS, I believe, negative 131. Times the complex conjugate of the current that's flowing through. So that's 13.106 with an angle of negative 11.432 degrees. Amps RMS. 152, okay. And that is 1408.636 angle negative 142.432 degrees volt amperes, and in rectangular form that becomes negative 1116.527 minus J 858.849 volt ampere. And while I'm at it, I will simply check our answers. So 687 point something, so that's right, that's right. What is the next thing? So for the J5 ohms, 0, 1073 and change, yep. 429.4, yep, 0, yep. Negative 214, yep. Negative 1116.5, 858, yep, so everything is correct. So we solved that problem and got all 5 of those complex powers, and the only voltage that we knew the entire time was our source voltage. So again, being able to understand and manipulate our complex power expressions to use our available information can vastly shorten the amount of time we need to be able to solve these guys. Using Ohm's law to get all of those voltages wouldn't have taken us long, but it would have been tedious. And again, it's more information that than we actually needed. So I like to use the alternative relationships, is I believe what I called them on the video lecture. to shorten the amount of time it requires me to do the circuit analysis. Okay, so that is WebWork 23 problem 3. Do we have any other questions we can look at?
Can we do 31 on practice exam winter 2020?
Winter 2020, number 31. All right, give me just a moment to find that guy. So let's see. Winter 2020, exam 3. And which problem did you say?
31.
31. Okay, so let me get a new sheet of paper. All right, so we are told that VC of t is equal to 13 cosine 10 to the 3t plus 22.6 degrees volts, and that C is equal to 225 microfarads. So we're asked to find the instantaneous power PC at t is equal to 7.8 milliseconds. All right, so our instantaneous power equation is going to be 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. Right now we have Vm and theta v. So we're going to need to be able to figure out what the current is through our capacitor as well. So we could say that VC as a phasor was 13 angle 22.6 degrees volts. The impedance of the capacitor, which is 1 over j omega c, is going to give us 1 over j times 10 to the 3 times 225 times 10 to the minus 6. So that is, let's see, 1 over let's see, 4.44444 repeating. That is what? How many ninths is that? I'll just leave it as this. Minus j 4.444 repeating ohms. And from this, our capacitor current, IC, is simply VC divided by ZC. So angle 22.6 divided by, that gives us 2.925 with an angle of 112.6 degrees amps. So now we have IM, which is this guy, and theta I, which is that guy. So you can put in everything that we're going to have. And I know right off the bat that theta V and theta I are separated by 90 degrees. You can do the math and figure it out. But I know that for a capacitor, the average power is supposed to be 0. So this whole first term, I'm not even going to bother writing down again. So PC is going to be 1/2 times my voltage, which is 13 volts, my current, 2.925 amps, times the cosine of twice 10 to the 3, 180 degrees over pi. My time is 0.0078 seconds plus theta V plus theta I. Close this guy off. $11.969 watts. Probably the most common mistake I would see on this problem or calculating the instantaneous power for any problem is forgetting to include that conversion factor. So omega is always expressed in radians per second. When you multiply that by time over here, that gives you an angle in radians. And since our phase angles are always expressed in degrees, it's very important that I remember to convert my angle in radians to degrees so that I get all of the units correct on my angles. Any other questions or comments regarding this problem? Any questions regarding another problem?
Can we do 33 and 34 in that same practice exam?
Sure, 33 and 34, let's see. So 33 and 34 is where I accidentally trick you guys into doing three-phase calculations. So all right, so we have the following circuit. Let's see, plus, minus, minus, plus. I'm going to draw it like this so it'll be less awkward looking. It's the exact same thing though. ZC and ZB. let's see, this guy is V1, this guy is V2, this guy is V3, and we're told that V1 is 138, angle negative 118, V2 is 173, angle negative 151, V3, stop, is 191, angle negative 24, VA is 3 plus J2, ZB is 4 minus J4, and ZC is 10 minus J3. All right, so for number 33, I ask you to find the average power absorbed by impedance ZA. So how I would approach this problem is I'm going to define a voltage here. Let's see, plus VA minus, like so, and I'm going to do KVL around this loop. So if I start in the bottom left-hand corner, I can see that V2 minus V3 minus VA is equal to 0. Everybody on board with me thus far?
Yes.
So I can rearrange this guy and find that VA is then just V2 minus V3, which gives me, let's see, 173 angle negative 151 minus 191 angle negative 24, 325 angle, excuse me, 325.885 negative 178.912 degrees volts RMS. And from this, I can see that SA, and this is going to use one of my alternative relationships, is simply the magnitude of VA squared divided by the complex conjugate of ZA. Do I need to derive that, or can I just use it?
You're good. You can just use it.
All right, so from this, I get 325.885 volts RMS squared divided by 3 minus J2 ohms which gives me 24507.931 plus J 16338.621 VA. We are asked to find the average power. So that's this guy. So PA is 24.508 kilowatts. Looks like on the test I have 24.503, so I introduced a little bit of rounding error somewhere, but being off by a couple on the thousandth degree or the thousandth place shouldn't be anything particularly wild there. I did notice that I have 24.503 kVA and 24.503 kVAR as possible answers. So this problem requires you to know how to do the math and then identify that the average power has units of kilowatts. Yeah. And problem 34 would be done in an extraordinarily similar way, except since we're looking for ZC, we would do our KVL loop around this guy and then do the exact same math effectively. We want the reactive power, so we would find the imaginary part. So do I need to do more on this problem, or are we good?
I'm good.
Alrighty, who's got another problem for me to look at?
Hey, Dr. Hartman.
Yes.
I was wondering if we could look at practice exam spring 2019,
Spring
number
20
35.
All right, so let's see. Spring 2019. Number 35, you said. All right, let's get a fresh sheet of paper. All right, so number 35 says that we have a 230 angle 0 volts RMS voltage source with an operating frequency of 50 hertz is used to supply power to two inductive loads connected in parallel. So I'm going to start drawing a little bit of a picture here. So here is our voltage source, 230 angle 0 degrees volts RMS at 50 hertz. And then we have it connected to two loads connected in parallel. So here will be load 1. And over here will be load 2. And load 1 draws 40 kilowatts at a power factor of 0.9 lagging. Load number 2 draws 25 kVA at a power factor of 0.78 lagging. And we want to know the value of the capacitor that would correct the source to 0.95 lagging. So we're told PF new is equal to 0.95 lagging. All right, we're trying to find C. So the power factor, so in order to do this, we're going to need to know the complex power of supplied by the source before power factor correction, S old, as well as the complex power supplied by the source after power factor correction, S new. So I would say that S old is simply, should be an equal sign, not a plus sign, the complex power absorbed by load 1 plus the complex power absorbed by load 2. So does anybody have any problems with that assessment? So the source has to supply as much power as the loads are absorbing. So from this, I can say that S load 1 is average power absorbed by load 1 divided by the power factor of load 1 with an angle of the inverse cosine of the power factor of load 1. And for load 2, we're going to have the apparent power with an angle of the inverse cosine of the power factor of load 2. Where again, the units of kilovolt amperes tell us in load 2 that we're already given the apparent power. So that's why we're not dividing by the power factor. So from this, I'm going to have which is going to look like, let's see, 40 divided by 0.9, angle inverse cosine 0.9 plus 25 angle inverse cosine 0.78, 69.040 with an angle of 30.478 degrees. kVA. And in rectangular form, that looks like 59.5 plus J, 35.017 kilovolt amperes. So that is my S old. S new, the complex power supplied by my source after power factor correction, is going to be the average power divided by PF new with an angle of inverse cosine PF new, which is 59.5 kilowatts divided by 0.95, I think, yeah. Inverse cosine of 0.95 is 62.631, angle 18.195 kilovolt amperes, and in rectangular form 59.5 plus J 19.557. S capacitance, so the complex power that's being absorbed by the capacitor is then simply S new minus S old. So that is 19.557 minus 35.017, negative 15.460. minus J 15.460 kVA. And so C is 15.460 kVA divided by my frequency, 100 pi, because 50 hertz times 2 pi is 100 pi radians per second, times my voltage drop across the capacitor, which is 230 volts RMS, quantity squared. So 15.460 times 10 to the 3 divided by 100 pi times 230 squared gives me 930.259 microfarads. So there's a little bit of rounding error on this guy as well, but none of the other answers are remotely close to that.
Thank you.
Okay, any other questions on any web work, exam problems, that kind of jazz? Anybody? All righty, well, looks like I am headed off to lunch. As I stated yesterday, I do have some office hours available this afternoon if anybody feels like they need a little bit of one-on-one time, but I'm going to try to limit those appointments to say 20 to 30 minutes per person tops, just because I have stuff I got to do. Okay, and other people may need help as well. All right, so I will have the Zoom meeting from yesterday and this review meeting. I will post them tonight so that those of you who are electing to take your exam tomorrow afternoon or tomorrow evening will have access to look through them and study and all that kind of jazz. And then, you know, you guys on Thursday will have a little bit more time. It's just the way it is. Some people got to take the test early. So unless anybody has anything else, I am out of here.
Hey, Dr. Hartman,
Yes, sir.
just a quick question about the exam. Did you want us to let you know what day, or does it really matter, or it doesn't really matter? It'll just be open those specific times and we can just whenever.
Yeah, it'll just be open those specific times. You can pop in and do it. I will not, so you can't take the test 3 times or anything like that and try to get a grade. You know, the first time you take it, that's your grade.
Awesome. Thank you.
I'm too lazy to figure out how to prevent people from taking it multiple times. So I'm just going to find the first one and then that's your score.
Cool deal.
All righty. I'll catch you guys, excuse me, later.